Right now, somewhere in the middle of the Pacific Ocean, a patch of seawater roughly the size of the continental United States is several degrees warmer than it should be. You can't see it from the shore. There's no dramatic wall of heat rising from the waves. And yet that quiet, invisible warming is enough to shift rainfall thousands of miles away, fuel or suppress hurricanes on opposite sides of the planet, push global temperatures to new records, and put the lives of millions of people and the survival of entire coral reef ecosystems on the line. This is El Niño, and as of the middle of 2026, it's back, and it's strengthening fast. In June 2026, NOAA's National Weather Service made it official. El Niño conditions have developed in the tropical Pacific. Sea surface temperatures in the key monitoring region known as Niño 3.4, a patch of ocean straddling the equator west of South America, had climbed more than 1.5 degrees Celsius above the long-term average, and climbing further. Forecasters now estimate roughly a 9 in 10 chance this event reaches at least strong intensity by autumn, and well over a 50% chance it becomes what scientists informally call a very strong or super El Niño, the same rare category that produced some of the most disruptive weather years in modern record keeping. Some climate models are going even further, suggesting this could be one of the most intense El Niño events ever recorded, potentially rivaling or exceeding the historic events of 1982 or 83 and 2015-16. To understand why a patch of warm water in the middle of an ocean can do all of that, we need to step back and look at how the entire Pacific actually works. Because the story of El Niño is really the story of how the ocean and the atmosphere are locked together in a single breathing system, one that occasionally takes a deep, disruptive breath. Under normal conditions, something called the trade winds blow steadily from east to west across the tropical Pacific, from the coast of South America toward Asia and Australia. Think of these winds as a giant conveyor belt sitting on top of the ocean. As they blow westward, they literally push warm surface water along with them, piling it up near Indonesia and the western Pacific. This is why, in a typical year, sea levels near Indonesia sit measurably higher than sea levels near Peru, and why the western Pacific is home to some of the warmest open ocean water on Earth, fueling towering thunderstorms and heavy monsoon rains across Southeast Asia and northern Australia. Meanwhile, back on the eastern side of the Pacific, near the coasts of Peru and Ecuador, the departure of all that surface water allows colder water from the deep ocean to rise up and take its place, a process called upwelling. That cold, nutrient-rich water is like fertilizer for the ocean. It feeds plankton, which feeds fish, which historically fed enormous fishing economies along the South American coast. This whole system, the winds, the warm water in the west, the cold upwelling in the east, is called the Walker circulation, named after the British scientist who first identified the linked patterns of pressure across the Pacific in the early 20th century. El Niño happens when this finely tuned system breaks down. For reasons scientists still don't fully understand in terms of exact triggers, though they involve complex interactions between ocean temperature, wind bursts, and pressure systems. The trade winds weaken. Sometimes they even reverse, blowing from west to east instead. Without that conveyor belt holding everything in place, the warm water that had been piled up in the western Pacific begins to slosh back eastward, like water rushing back across a tilted bathtub after you stop blowing on one end. This warm water travels eastward through giant underwater waves called equatorial Kelvin waves, gradually flooding the central and eastern Pacific with unusually warm surface water. At the same time, the upwelling of cold water off South America weakens or stops entirely, because there's no longer a wind-driven mechanism pulling deep water to the surface. The net result? The eastern Pacific, normally cool, becomes warm. The western Pacific, normally the warmest patch of ocean on the planet, becomes relatively cooler. And the entire atmospheric engine that depends on that temperature contrast starts running differently. This is the part people often misunderstand. El Niño isn't really about a single number, a single degree of warming in one patch of ocean. It's about what that warming does to the atmosphere above it. Warm ocean water evaporates more, and that moist, rising air feeds thunderstorms. So as the warmest water shifts from the western Pacific toward the central and eastern Pacific, the location of the biggest storm systems shifts with it. And because the atmosphere is a single connected fluid, wrapping around the entire planet, moving the location of a major heat and moisture source in the tropical Pacific sends ripples, technically called teleconnections, cascading through weather patterns thousands of miles away. This is how a warm patch of ocean near the equator can mean a wetter winter in California, a drought in Indonesia, unusual storms in East Africa, and a quieter hurricane season in the Atlantic, all at the same time, all because of the same underlying shift. Let's look at some of those specific consequences, because they are not abstract. They are written into the way entire regions plan their agriculture, their water supplies, and their disaster preparedness. During El Niño winters, The jet stream over the North Pacific tends to shift southward and strengthen, dragging the storm track across the southern United States. This typically means a wetter, stormier winter across the Gulf Coast and the southern tier of states, with increased risk of both heavy rain and, in some cases, unusual snow events, while the Pacific Northwest tends to be drier and milder than average. Given that current forecasts point toward a strong or very strong event peaking around the 2026-27 winter, meteorologists studying the atmospheric setup have already started drawing comparisons to past El Niño winters that brought significant flood risk to California, the kind of pattern where corresponding atmospheric river storms slam into the state in quick succession, overwhelming reservoirs and rivers that had been starved of rain just a year or two earlier during the preceding La Niña. Move south toward the Horn of Africa and parts of Central Asia, and El Niño often brings increased rainfall, sometimes dangerously so, given that these are regions where the underlying infrastructure, drainage systems, and emergency response capacity are not always built to handle sudden deluges. Meanwhile, across Indonesia, Australia, the Caribbean, Central America, and northern South America, the pattern usually flips toward drier than average conditions. For Indonesia, and Australia specifically, this isn't a minor inconvenience. Reduced rainfall during El Niño years has historically been linked to severe droughts, lower crop yields, and dramatically increased wildfire risk, since drier vegetation simply burns more easily and more extensively. The 2015-16 Super El Niño, for comparison, was associated with widespread fires across Indonesia that released enormous amounts of carbon into the atmosphere and blanketed entire regions in smoke for weeks. Then there's the ocean itself and the hurricanes that spin up across it. El Niño has a curious split personality when it comes to tropical cyclones. In the Pacific Basin, the extra warm water and altered wind patterns tend to enhance hurricane and typhoon development, sometimes significantly. But in the Atlantic Basin, El Niño does something almost protective. It strengthens upper-level winds in a way that creates wind shear, essentially tearing apart developing hurricanes before they can organize and intensify. This is one reason NOAA's 2026 outlook for the Atlantic hurricane season leans toward below normal activity, even as forecasters simultaneously warn of an unusually active and potentially historic El Niño building in the Pacific. It's a strange kind of trade-off written into the physics of global wind patterns. Calmer hurricane seasons for the Atlantic coast, but potentially more vigorous storm activity across parts of the Pacific. Beneath the waves, the consequences can be just as severe and arguably more permanent. Coral reefs are extraordinarily sensitive to temperature. Most reef-building corals live within a remarkably narrow thermal comfort zone, and when surrounding water temperatures climb even 1 or 2 degrees Celsius above the normal seasonal maximum for an extended period, corals begin to expel the colorful algae living symbiotically in their tissues, the same algae that provide them with both their color and a significant portion of their food energy. This is coral bleaching, and it leaves the coral skeleton stark white and starving. Corals can sometimes recover from short bouts of bleaching if temperatures drop back to normal quickly enough, but prolonged heat stress kills them outright. The El Niño event of 2015-16 triggered what scientists call the third global mass coral bleaching event, the longest and most widespread episode of coral heat stress ever recorded up to that point, affecting reefs, from the Pacific to the Indian Ocean to the Caribbean almost simultaneously. The 2023-24 El Niño then drove a fourth global mass bleaching event, and researchers studying reefs in the eastern tropical Pacific have documented sea surface temperatures during that event reaching levels never previously recorded at some long-term monitoring sites, with bleaching prevalence among certain coral species exceeding a third of all colonies surveyed. With a potentially very strong El Niño now building through 2026 and into 2027, marine biologists are bracing for the possibility of yet another mass bleaching event, layering additional stress onto reef ecosystems that, in many cases, are still trying to recover from the last one. Reef scientists describe this as one of the most worrying trends in the data. Bleaching events used to be separated by a decade or more, giving reefs time to regrow and recover, but as both El Niño frequency and background ocean warming from climate change have increased, those recovery windows have been shrinking. This brings us to a crucial point, one that's easy to misunderstand if you only think of El Niño as a standalone weather event. El Niño does not, by itself, get stronger because of human-caused climate change. The World Meteorological Organization has been explicit about this. There's no clear evidence that climate change is increasing how often El Niño events occur or how intense the ocean temperature anomaly itself becomes. But that's almost beside the point because El Niño doesn't operate in isolation. It operates on top of an ocean and atmosphere that are already warmer than they used to be, decade after decade, due to the buildup of greenhouse gases. So when El Niño adds its own temporary spike of heat on top of that elevated baseline, the combined effect can push global temperatures into genuinely uncharted territory. This is exactly what happened in 2024, which became the hottest year ever recorded in modern instrumental history, a record driven by the combination of the powerful 2023 to 24 El Niño and the steady underlying warming from human greenhouse gas emissions. Scientists describe El Niño as a kind of amplifier, not a cause, but a multiplier, that takes existing warming and temporarily turns the dial up further, often making global average temperatures noticeably higher in the year during and immediately following a strong event. Given that the current 2026 El Niño is forecast to potentially rank among the strongest ever observed, with model ensembles showing a striking convergence, the overwhelming majority of forecasting models now point towards strong or very strong intensity by autumn 2026. Scientists and climate agencies are watching closely to see whether 2026 or 2027 might challenge or exceed the temperature records set in 2023 and 2024. It's worth pausing here to appreciate the scale of what's actually happening physically. The ocean covers about 70% of Earth's surface and holds a staggering amount of heat compared to the atmosphere. More heat in the top few meters of the ocean alone than in the entire atmosphere above it. When a temperature anomaly of even 1 or 2 degrees develops across a region of ocean spanning thousands of kilometers, the amount of additional thermal energy involved is almost incomprehensibly large, equivalent to the energy released by detonating enormous quantities of explosives every single second, sustained for months. That energy doesn't just sit there. It gets transferred into the atmosphere through evaporation and heat exchange, and it's that transfer, multiplied across an ocean basin the size of the Pacific, that reshapes weather patterns across the entire globe. It's also worth remembering how scientists actually detect and track something this vast and largely invisible from the surface. Much of our understanding comes from a network of moored ocean buoys scattered across the tropical Pacific, continuously measuring sea surface and subsurface temperatures, paired with satellite measurements of sea surface, height, since warmer water expands and literally makes the ocean surface bulge slightly upward in affected regions. Combine that with satellite measurements of cloud patterns, wind speed and direction, and atmospheric pressure differences between Tahiti and Darwin, Australia, a comparison meteorologists have used since the early 20th century to track the so-called Southern Oscillation, and you get a remarkably detailed real-time picture of an ocean atmosphere system in flux. This is why agencies like NOAA, the World Meteorological Organization, and research institutions around the world can issue monthly updates with increasing confidence as an event develops, even though predicting the exact peak strength and timing months in advance remains genuinely difficult, partly because of what scientists call the spring predictability barrier, a period early in the year when El Niño forecasts are historically less reliable due to the natural transition happening in ocean conditions at that time. Step back far enough, and there's something almost humbling about all of this. A temperature shift of just 1 or 2 degrees in a patch of ocean most people will never see or sail across is enough to redirect monsoons, fill or empty reservoirs on opposite sides of the world, determine whether hurricane season is quiet or catastrophic, and decide whether millions of tons of living coral survive or bleach into ghostly white skeletons. It's a vivid reminder that Earth's climate isn't a collection of separate regional weather systems. It's one single interconnected machine where the ocean and the atmosphere are locked in a continuous conversation, and a change in one corner of that conversation echoes everywhere else. El Niño has been doing this for thousands of years, recorded in coral growth bands, ice cores, and the journals of South American fishermen who, centuries ago, simply noticed the water near their coast turning strangely warm around Christmas time, and gave the phenomenon its name, the Little Boy, in honor of the Christ child. What's different now isn't the existence of El Niño itself, it's the stage on which it's performing. Each new event arrives on top of a planet that is, on average, warmer than it was a decade ago, and warmer still than it was a century ago. So as the 2026 El Niño builds toward what could be one of the most powerful events on record, the question scientists are really asking isn't simply how strong will this one be, but what does it mean to layer an extreme natural cycle on top of an already shifting baseline? That warm patch of water in the middle of the Pacific will eventually fade, as it always does, typically within 9 to 12 months. The ocean and atmosphere gradually settling back toward equilibrium, or sometimes swinging the other direction entirely into a cooling La Niña. But the patterns it sets in motion this year, the floods, the droughts, the fires, the bleached reefs, the record-breaking temperatures, will linger in ecosystems and communities for years afterward. It's a strange kind of power for something so quiet and so far from shore, a reminder that on this planet, even the stillest stretch of open ocean is never really still at all.